Hello everyone, and thanks for watching Edupedia World Videos. This is the second video on the topic of inverse trigonometric functions, and in this video we'll see some properties of these types of functions. So there are certain categories in which the properties can be grouped, so I'll just label them as A, B and C. So A category would be formulas of the type of sine inverse 1 by x is equal to cosec inverse of x. Right. Now we know the domain of cosec inverse of x, that is r minus 1 to 1. So obviously mod x is greater than equal to 1 is the same as saying r minus 1 to 1. If this was a closed bracket, there would be no equal to sign here. I explained that in the previous video. Right. And if mod x is greater than equal to 1, mod of 1 by x is less than equal to 1, which is the domain of sine inverse x. Right. So this is the first formula. I'll write the other two, and I'll prove one. You can try the proofs of the other two. So then you have the formula cos inverse of 1 by x is equal to sec inverse of x. And again, you need to know the proper domains. So in this case, again, it will be mod x greater than equal to 1. And then you have, you guessed it, tan inverse of 1 by x is equal to cot inverse of x. And obviously the domain of both cot inverse x and tan inverse is r. But since you have a 1 by x term here on the left hand side, we'll remove minus 0. These are just the domains in which these equations are valid, because we need to know when these equations are valid. If x is any other value, some of these might not even be defined, but even if they are, the equations might not be valid. So let me just prove the first one. If sine inverse 1 by x is equal to y, that means 1 by x is equal to sine y. By the way, how did I get this equation from this? I took the sine on both sides and I used the equation sine or sine inverse something is something. And basically that's an equation I told you about. So sine inverse of sine x is equal to sine of sine inverse x is equal to x if it is within the normal intervals. I'll just write that. And you'll know what that means. For example, when we are talking about sine x, the range should be, the domain should be between minus pi by 2 and pi by 2. Otherwise, these formulas don't hold. For example, we talked about in the first case, if x is equal to 390 degrees, then sine x is half. Sine inverse of half is actually 30 degrees. So sine inverse sine x is not equal to x when x is 390. But it is equal to x when x is between minus pi by 2 and pi by 2. Right. So whatever the normal domains are, they are different for each of these functions. The ranges for the inverse and the domains for the actual trigonometric functions. As long as the argument is within those nice intervals, these formulas will be valid. And that's why the first thing I did when writing these formulas was write down what the values of x can be. And as long as these are the values of x that are possible, we will have sine of sine inverse 1 by x will always be 1 by x. Right. So I'll keep using these, and this goes for all of them. Tan inverse of tan x is equal to x as long as x lies between minus pi by 2 and pi by 2. If x is outside this range, then tan inverse of tan x might not be equal to x. Right. For example, if x is 360 plus 45 degrees, then tan x is 1. Tan inverse of 1 is 45 degrees. So they are not the same. Right. But within the nice domains which we've already defined for each function, we'll do. That's why it's a little bit hectic in inverse trigonometric functions, because the domains and the ranges are as important as the function, because otherwise the formulas might change in many occasions. So right now we are just working in the nice domains and the nice ranges, so we don't have to worry about anything. This means x is equal to cosec y. Now you take cosec inverse of both sides, you'll get cosec inverse of x is equal to cosec inverse of cosec y, which is y. So sine inverse 1 by x is equal to cosec inverse x. Right? You can try to do the other two in the same way. Right? So there's another category which has to do with taking the inverse of the argument. And since there are 6 trigonometric ratios which can be grouped into 3 groups of 2, sin x with cos x, tan x with cot x, and sec x with cosec x, or sin x with cosec x, cos x with sec x, and cot x with tan x, you'll have 3 formulas in all of these categories. So category B would be sine inverse of minus x is equal to the negative of sine inverse of x. But again, x has to be within the nice domain. In this case, it is between minus 1 to 1. Right. Similarly, tan inverse of minus x is equal to minus tan inverse of x. And cosec inverse of minus x is equal to the negative of cosec inverse of x. For this, x can be r, because the domain of tan x is r, and for cosec x the domain is r minus 1 comma 1. So basically mod x greater than equal to 1. This is the same as r minus 1 to 1. Right, this is what we wrote in the first video. Now we'll use this because it's simpler to write. So I'll just prove one of them. If sine inverse of x is equal to sine inverse of minus x is equal to y, that means minus x is equal to sine y. That means x is equal to sine of minus y, which means sine inverse of x will be sine inverse of sine of minus y, which will be minus y. Right, again we are working in the nice domain of minus 1 to 1. So obviously sine inverse minus x is y, then sine inverse x is minus y, which is minus of sine inverse of minus x. Right, and this is sort of what is to be expected because sine x is an odd function. Right, so sine inverse x is expected to behave in a similar fashion. Right, so and the same for tan x and cosec x. The next category is obviously for the other 3, but this is where things get a little tricky. So cos inverse of minus x, you might think it's minus cos inverse x, but it's not actually. It's pi minus cos inverse of x. Right, so let's just do this first. In this, x is between minus 1 to 1. Right, so let's try to prove this, then I'll write the other 2 similar equations. Let's take cos inverse minus x is equal to y. This means minus x is equal to cos y, which means x is equal to minus cos y. Now what happened in the previous case here, x was minus sine y, which just meant that it was sine of minus y. But that's not true for cos x, right? So x is equal to minus cos y basically means x is equal to cos of pi minus y. Right, and from this what you get is cos inverse x is equal to pi minus y. That is pi minus cos inverse of minus x. Right, so here's where this factor pi comes from. That's why cos inverse minus x is equal to pi minus cos inverse x. Now x is between minus 1 to 1, which means cos inverse of that will have to be between 0 and pi. Right, so that means y is between 0 and pi. Now if y is between 0 and pi, pi minus 1 is also between 0 and pi. Right, and that's why this thing works, because pi minus y is between 0 and pi. I could have written 3 pi minus y here, but then 3 pi minus y would not be between 0 and pi, so we could not use the standard formulas cos inverse cos x is equal to x. right? And that's why this pi minus y factor comes here. I'll write the other two, which you can derive by yourself. Sec inverse of minus x is equal to pi minus sec inverse of x, and in this case mod x has to be greater than equal to 1, and cot inverse of minus x is equal to pi minus cot inverse of x, and in this case x can be any real number. Now let's look at some more formulas, and now these will be some of the most important formulas you use in inverse trigonometric functions. Sine inverse x plus cos inverse x is equal to pi by 2 for x between minus 1 to 1. I'll write the other two as well, and then I'll try to derive the first one. Tan inverse x plus cot inverse x is equal to pi by 2, but now x can be any real number, and sec inverse x plus cosec inverse x is equal to pi by 2 again, but now mod x has to be greater than equal to 1. So first, let's prove the first one. I'll prove that, you can prove the other two. So let's take sine inverse x is equal to y, which means x is equal to sine y, which means x is equal to cos of pi by 2 minus y, which means cos inverse x is equal to pi by 2 minus y, and y is obviously sine inverse x, so from that we have proved that sine inverse x plus cos inverse x is equal to pi by 2. Right. So this and the other two equations are equations you'll frequently be using, and so you can try to derive the other two on your own. A few more important properties. You know the formula for tan a plus b, right? Tan of a plus minus b, I'll write it for both of them, is equal to tan a plus minus tan b by 1 minus plus tan a tan b. If this is a plus, then the numerator has the plus, the denominator has a minus. If this is a minus, the numerator has a minus and the denominator has a plus. Right. So from this we can get two properties. Tan inverse x plus tan inverse y is equal to tan inverse of x plus y by 1 minus xy, and tan inverse x minus tan inverse y is equal to, you guessed it, tan inverse of x minus y by 1 plus xy. Okay, and how do we prove these? I'll just prove one of these. Right. So let's take tan inverse is equal to tan inverse x is equal to a, tan inverse y is equal to b, which means x is tan a and y is tan b. Right. And now we can just look at this side. This is basically a plus b. So you take the tan of that, you'll get tan a plus b. Tan of a plus b, which you know is equal to tan a plus tan b by 1 minus tan a tan b. So that will be equal to x plus y by 1 minus xy. Right. Similarly, you can do for the other one. And there's a final set of properties. 2 tan inverse x is equal to, now there are three separate formulas for this. Sine inverse of 2x by 1 plus x squared, and then you have cos inverse. I should be writing an equal to sign in between, but I won't because the domain in the three are different. I'll explain that in a minute. And it is also equal to tan inverse of 2x by 1 minus x squared. The first one is valid when mod x is less than equal to 1. The second one is valid when x is greater than equal to 0. And the third one is valid when mod x is less than 1. Right. So I'll try to prove the first one. You can do the second and third, and you have to be careful in this case about the ranges. So you just proceed in the standard way. You take tan inverse x is equal to y, which means x is equal to tan y. And then you look at sine inverse of 2x by 1 plus x square, which becomes 2 tan y by 1 plus tan square y, which you can simplify it. 2 sine y by cos y by 1 plus tan square y is 1 plus sine square y by cos square y. So you take cos square y here, it becomes 1, and this cos square y goes up, multiplies by cos y. So basically you get sine inverse of 2 sine y cos y, or you get sine inverse of 2y. Sine inverse of sine 2y, which is equal to 2y, which is equal to 2 tan inverse x. And you can prove the other two in this way, but where the ranges come into play is that the domains of these need to be correct. So if there is something within sine inverse, then that something has to lie between -1 and 1, right? Because the domain of sine inverse is between -1 and 1. So 2x by 1 plus x squared should be less than equal to 1 and greater than equal to -1. So if we just take less than equal to 1, that means 1 plus x squared greater than equal to 2x. That means x minus 1 whole squared. This should be greater than 0. But this is valid for all x, right? So this doesn't really tell us anything. But then we look at the relation between these two terms. Sine inverse x, this term has to be between -1 and 1, but the range of sine inverse x is between -pi by 2 and pi by 2. But the range of tan inverse x is also between -pi by 2 to pi by 2, so the range of 2 tan inverse x is between -pi to pi. Right, but we don't want that. We want the range of 2 tan inverse x to be -pi by 2 to pi by 2. Right, that means tan inverse x should be -pi by 4 to pi by 4. When is tan inverse x pi by 4? When x is equal to 1. Right, so it has to do with this, because if x is greater than 1, tan inverse x will be greater than pi by 4, which means the LHS will be greater than pi by 2. No value of sine inverse will ever be greater than pi by 2. That's why mod x has to be less than 1. Similarly, you can look at the other two. Technically I could write this is equal to this is equal to this is equal to this, but I hesitate because the three domains are different. So this is one identity. The second will be 2 tan inverse x is equal to this thing when mod x is greater than 0, right? And then 2 tan inverse x is equal to this thing when mod x is less than 1. So whenever you're solving questions involving inverse trigonometric functions, you have to remember the properties and the ranges and domains, but also you have to be extra careful about every range and domain. So that's another element of difficulty that has been introduced into the problem. But generally, the more you practice with problems involving inverse trigonometric functions, the easier it will become and the quicker you'll get in being able to solve them. Thank you.